Good afternoon, everybody. It looks like it's time to begin, so we will. Just a reminder that there's homework up here from last time, so if you didn't pick yours up, make sure you get yours. The class in general really did fine. I mean, I gave you a few hints last Monday, I guess, which I thought were going to be some of the bigger sticking points, and indeed they were. Most students did fine. I think the biggest error really is just remembering that if you have a first law problem for a closed system, you need to use heat transfer equals change in internal energy plus work, except if you have a constant pressure process, then you can combine the boundary work with the internal energy change, and the equation really just becomes heat transfer equals change in enthalpy, and then plus any other forms of work. So that was probably one error that I saw a lot. Also, there was that one problem where you had a paddle wheel and an electric resistance work, but then it was still a piston cylinder device, and there were quite a few students that just seemed to forget that there was the piston cylinder device, meaning that there was some boundary work. So several of you forgot to include the boundary work. A lot of students, since it was a constant pressure problem, used heat transfer equals change in enthalpy plus the other work, and that was correct. That means you didn't forget the boundary work, that you did indeed include it with the internal energy change terms. So anyway, the solutions were posted Wednesday. They'll, of course, be there. All the solutions from the first week are still outside my office, so look at those before your test Monday. And I'll set aside time, the last 10 minutes or so, to answer questions about the midterm and, go over in a little more detail.
So the problems on this homework that's due Wednesday, the chapter 4 problems, are they going to be on the test as well? Or
The work you're getting back today, yes, but all of this week's material, no.
Well, I'm not the one that's due this coming Wednesday. That's chapter 4.
Next week, no.
Okay.
No, anything we covered this week. Basically, only through section 4.2, I think that's what it says on the syllabus, which would be the first law problems for a closed system, but not including the use of specific heats for ideal gas problems or solid and liquid problems. So, yeah. Just through last week's homework that you turned in Wednesday, that I just returned to you today. That'll be part of it.
In what cases are piston cylinder devices not constant pressure processes?
The only time they're really constant pressure is if it's a vertical frictionless device where the piston is free to move up and down.
Okay.
If there's any work being done by a system or a person, if anybody's grabbing that piston and pushing it, like if it tells you that it's a piston cylinder device and the gas is being compressed, the implication is that somebody has hold of that piston and is pushing it and compressing the gas. So that would not be a constant pressure problem. It's only if the piston is free to move under its own weight, and it has to be vertical. The fact that the weight is constant and that the area is constant and the atmospheric pressure above it is constant tells you that the force of the piston, therefore the pressure of the cylinder, also has to be constant.
So then, in what case can it be a constant volume process? Because if the piston is constantly moving up and down,
Then it's not a constant volume
so
process.
it should never be. Okay.
No. I mean, unless the piston is stationary, like we looked at some problems where you have a piston cylinder device that has a set of stops. If the piston is bumped up against the stops such that it acts as a rigid container, a rigid vessel, well, then it's a constant volume process. So, I mean, I guess that would be an example of where within a piston cylinder device it would be a constant volume, but that's a very special case. By the way, those piston cylinder devices with stops are essentially modeling internal combustion engines. If you have a piston in an internal combustion engine, you'll compress the air-fuel mixture, and then when you get to the top, there's no physical stop, but because of the linkages, it physically can't move any further. That's where the combustion process takes place at constant volume. That's where your heat input is. And then at the end of that, you have a high temperature, high pressure gas that pushes the piston down to create work. So these piston with stops problems is really just one way of beginning to look at a future internal combustion engine problem. Okay, all right. Last time we began looking at the first law for open systems, and in fact we didn't really even look at the first law, we looked at the conservation of mass or continuity equation associated with the first law. Many of these problems are indeed going to be well, not many of them, all these problems are going to require that we somehow use the continuity equation or some version of the continuity equation. Most of these problems that we'll be dealing with are indeed steady flow problems, meaning that whatever mass flows in is the same as what flows out. And we're going to have to utilize these conservation of mass principles along with the appropriate first law equation, which I'll develop for you today, when we solve these open system, or if we will, control volume problems. So the first thing I want to do today is just go through a couple of really basic example problems, but they will be typical of a portion of a first law problem. So this first problem is up here. It's 5.7 from the previous edition, from the 7th edition, so you're not going to find it in your book. You've all seen it. It basically says now that you have air entering a nozzle steadily. In fact, when it uses the word steadily, that's the author's way of saying that it's a steady flow process. So it enters steadily with the density of 2.21 kilograms per cubic meter and a 40 meter per second velocity, and then it leaves with a density of 0.762 kilograms per cubic meter and a velocity of 180 meters per second. It says if the inlet area is 90 square centimeters, find the mass flow rate through the nozzle and find the exit area. So, I would show this with a nozzle. Maybe not the best nozzle I've ever drawn, but certainly good enough. It has air. We've got inlet and exit conditions. I could use I and E, but as I mentioned last time, I'll do the same as the author. We'll just use 1 for inlet and 2 for exit. This does not mean initial and final state. Within the control volume, it means the entering and exiting state of the control volume. We're given at the inlet side that the density is 2.21 kilograms per cubic meter, and we're also given the velocity at the inlet of 40 meters per second. And then on the exit side, we're given a different density, 0.762 kilograms per cubic meter, and the exit velocity is quite a bit higher, as is the case with all nozzles, 180 meters per second. We're also given the inlet area, so A1 is 90 square centimeters. It always makes sense to convert this into square meters. We know there's 100 centimeters per meter, and therefore 10,000, 100 squared, if you will, square centimeters per square meter. So you can write this as 0.009 cubic meters. So that's the inlet, and we're trying to find the mass flow rate, and we're trying to find the area at exit. Now, quite frankly, there's not a whole lot to do in this problem. I mean, we remember that the mass flow rate is velocity times area over specific volume, and it's a steady flow problem. As such, the mass flow rate at the inlet is the same as the mass flow rate at the exit. This mass flow rate, well, we can only really calculate it at the entrance, right? We only have data at the entrance, so we have to find it at the entrance, 0.1. So we'll just write this as V1A1 over specific volume. Of course, it's also going to equal V2A2 over V2. In other words, m dot at the inlet equals m dot at the exit. Now, let's further note that we haven't been given any specific volume data, so nobody should worry about that. We know it's just the inverse of the density. So we could really just write this then as velocity area times density at the inlet equals velocity area times density at the exit. In fact, now you can see that we can solve for both of the things that we're looking for. We can solve this first equation directly for the mass flow rate, right? We have velocity, area, and density. And then once we have that mass flow rate, we can plug it back into the equation, and we know the velocity and the density at the exit, so we can solve for the area at the exit. So it's really pretty straightforward. So let's just do that. The velocity at the inlet is 40 meters per second. The area is 0.009 square meters. The density is 2.21 kilogram per cubic meters. You can see that everything cancels except for kilograms per second, and we end up with 0.796 kilograms per second. So there's the mass flow rate. And then we just plug it right back into the equation above. Velocity, area, density, all at state point 2. So we're given the velocity as 180 meters per second. The area at point 2 is my unknown. The density is given as 0.762 kilograms per cubic meter. And we could just solve this now for the exit area, and we get 0.0058 square meters. Or if you prefer, we can divide by 10 to the 4th, and we get 58 square centimeters. So this is a pretty typical beginning to any first law problem. In many first law problems, we need to find mass flow rate. We maybe need to find some geometry information like the area to further the problem when we solve the first law. So these are not first law problems, but you're going to have mass conservation problems in many of the first law problems, and you'll have to do them right at the beginning of those problems. Another thing I might note is that there are many different variations on the theme of this problem. Sometimes you'll be given a diameter, in which case you have to use pi over 4d squared to get the area. Sometimes you'll be asked for the diameter of the pipe as opposed to the area of the pipe that's connected to this nozzle. So, just think about some of the slight variations to this problem. Well, great. Any questions? All right, so that one's straightforward. Let's look at another one that's also straightforward, but maybe not quite as straightforward. So this one is also from the 7th edition. So it's a little bit different. All right, so this one is 512. We have the 7th edition. So it's over here. Let me again read it. It says that air enters the 1 square meter inlet of an aircraft engine at 100 kilopascals, 20 degrees C, with a velocity of 180 meters per second. It says determine the volumetric flow rate in cubic meters per second at the engine's inlet and the mass flow rate in kilograms per second at the engine's outlet. So again, it sounds pretty straightforward. So let's just show an aircraft engine. You've all seen them. They kind of look like that, and they hang off the wing of an airplane. Again, we have an inlet and an exit at state points 1 and 2. We are assuming that it's air, although in reality we're going to mix the air with fuel, we're going to burn it, and you'll have combustion gases that are really going to leave this engine. But as we'll find in this class, we're always going to assume, let's just call it an air standard type of process. In other words, even though we know it's really air and fuel and combustion gases, we're just going to assume it's all air, especially as we're first beginning to learn this material. All right, so that's the diagram. As far as the data that's been given, so we're given the area at 1, the square meter, pressure at 1, 100 kilopascal, temperature of 20 degrees C, and the velocity of 180 meters per second. And we know absolutely nothing about the discharge side. It turns out we don't need it. Now you may say, well, how can we not need it? They've asked me for the mass flow rate at the engine's exit, right? But this is a steady process, right? We're not accumulating or diminishing the mass within the engine. Whatever comes in goes out. So we know that the mass flow rate in and out is going to be the same, like essentially all these problems are. Anyway, what we're asked to find is the volumetric flow rate at the inlet. So V dot 1 is unknown. And we need to find the mass flow rate at the exit, which we know is really M dot 1. So you can see that we really don't need to know anything about the exit. It just doesn't matter. All we need to do is use the appropriate equations to find what we're looking for. Now, we know that mass flow rate is velocity times area over specific volume. And if we rearrange this, If we rearrange this, we could just write this as mass flow rate times specific volume equals velocity times area. But as we have already seen, in the same way that mass is volume over specific volume, mass flow rate is volumetric flow rate over specific volume. So then we saw this last time. This is really just V dot, right? So the mass flow rate times specific volume is a volumetric flow rate. So we have V dot equals velocity times area. And if we're trying to find the volumetric flow rate at the inlet, then we have to use all of our data at the inlet. So this really has to have a V1 and an A1 on it. So that's how we're going to find the volumetric flow rate. With regards to the mass flow rate, well, we need to use the equation that is our general equation, just mass flow rate equals velocity times area over specific volume. And we don't know the specific volume, right? We do have the velocity and the area, but they've given me the pressure and the temperature for this problem. So as long as we have those two properties, we should be able to either use the ideal gas equation of state if it's an ideal gas to get the specific volume, right? Or we should be able to use the compressibility chart to find the specific volume if it's not an ideal gas. Hopefully it'll be an ideal gas because it'll make things go a lot more smoothly, well, at least quickly. So first things first, why don't we just calculate the volumetric flow rate? The volumetric flow rate is, again, area, well, velocity times area. So 180 meters per second times 1 square meter equals 180 cubic meters per second. And that's really all there is to it. So that one is pretty straightforward. With regards to the mass flow rate, well, again, it's straightforward too, but we need the specific volume. So let's ask ourselves, is it an ideal gas? And the way we know it's an ideal gas is if the reduced temperature is greater than 2, or the reduced pressure is much less than 1. So, by the way, nothing in this problem says that it's an ideal gas. We just know that it's air, which is a gas. So you can't just automatically assume that it's an ideal gas. There will certainly be some problems where the only way we can solve them is to assume that it's an ideal gas, in which case just assume it's an ideal gas. But in this particular case, we would really like to use most accurate value of specific volume that we can. So what we would want to do then is first go into our property tables, table A1, and what we'll find is the critical point temperature. And the critical point temperature is actually 132.5 Kelvin. Now, I could bring the property table up on the other board. I don't think we need to do this at this point. We've seen the property data. We know how to find critical point data. So this is our critical point temperature. So the reduced temperature is just T over the critical point temperature. 20 degrees Celsius has to be converted into Kelvin. If you don't convert it into Kelvin, it's wrong. You have to convert it to Kelvin. There's no choice. So we convert it into Kelvin, and that becomes 293.15 in the numerator. We go through a little bit of mathematics, and actually, I didn't even do the math. I just know that the numerator is more than twice the denominator, so it's definitely greater than 2, and therefore, yes, it's an ideal gas. So, ideal gas. And once we have concluded that it's an ideal gas, well, that makes things pretty easy, right? We know that PV equals RT, and therefore V equals RT over P. If we go back into the same table A1, we get 0.287 kilojoules per kilogram per degree Kelvin as R. So let's just note that this is also from table A1. We multiply by the temperature, and again we have to convert from Celsius into Kelvin, so we've already done that above. We know it's 293.15. And the pressure is going to be 100 kilopascals. And as usual, we look at these units for this particular problem, and it seems like there's a problem, right? Oh, by the way, this should say 1, right? V1 equals our T1 over P1. We're using the inlet conditions to find the inlet specific volume. Anyway, the units don't look quite right, but we've already done this at least twice, maybe 3 times. Remember, a kilonewton per square meter is the same thing as a kilopascal, and a kilojoule is the same thing as a kilonewton meter. So the units actually do work out properly, right? Everything cancels. The only thing that doesn't cancel are cubic meters, which are in the denominator of the denominator, in other words, in the numerator, and the mass units of kilograms remain as well. Everything else just cancels. So we go through a little bit of math, and we end up with 214.1 cubic meters. Uh-oh, I put kilograms and it's seconds. Where'd my time units go? Oh, no, I'm sorry, that's right. This is right. I just wrote down the wrong number here. We end up with the specific volume, yeah, sorry about that, 0.8409. I was just one step ahead of myself. Anyway, we have the specific volume, so the last step then is to finish the problem by finding the mass flow rate. And again, the mass flow rate is velocity area over specific volume. And we're doing this at state point 1. So again, just plug in all the right numbers. 180 meters per second, 1 square meter, 8409 meters cubed per kilogram, and here we have kilograms per second. So our units are the right units for mass flow rate. We go through the math, and this is our 214.1. So this would just give you an illustration, again, of how to use the continuity equation and the other related mass flow rate equations to solve a steady flow problem for a control volume. Pardon me. So any questions on this? All right. Now for the fun part. Okay, again, any questions? Remember, none of this is going to be on your exam. Well, not on this exam. Certainly be on the exam eventually. Okay. We've seen now how, maybe I should wait a second. It seems like people are still kind of finishing writing out this problem. Again, are there any questions on this problem? In fact, any questions at all, just in general, about mass, flow rate, continuity, and all that? All right. So the next thing we're going to do then is the actual first law analysis. So first law, which we can also call an energy balance. A lot of people just use the phrase energy balance. I've used that phrase in some classes, but this is really our first law analysis of an open system. And remember again, an open system, we can also call it control volume, so I just use CV as my abbreviation for control volume. Now, there are a lot of problems where it just simply doesn't make any sense for us to use the closed system analysis. If we have a process that involves flow, all those different processes that I've mentioned, pumps, turbines, compressors, nozzles, diffusers, heat exchangers, mixing chambers, any of that, they're all discussed in this section, which is now section 4.5 in your textbook. Those are not constant mass problems, right? They're not sealed rigid vessels. There's definitely mass that's flowing, so we have to use this open system approach. Now, you may also wonder, well, why are we even doing this? Keep in mind that in thermodynamics, you're trying to find relationships between thermodynamic properties, relationships dealing with things like temperature and pressure. If you're going to design a pump, for example, how are you going to know how thick to make the metal wall of that pump unless you know what kind of pressures you're going to see within that pump? You don't get those pressures from mechanics analysis. Those pressures come from the thermodynamics. Let's say you need to determine how much cooling to provide for a pump. I mean, pumps generate a lot of heat. because sometimes you have very high temperature components or fluids passing through them. You don't want the bearings to overheat. You don't want the pump to overheat. You need to do some sort of heat transfer analysis so you can figure out how much heat you need to remove from that system. Well, how do you do that without thermodynamics, right? You need to know the heat transfer rates. You need to know the temperatures. So there's a whole lot to thermodynamics than just trying to figure out how thermodynamic properties relate to each other, right? This is really fundamental to the mechanical design of all real pieces of equipment and systems. And the most common types of systems are not sealed tanks or piston cylinder devices. They're open systems, right? Those devices, right? If you look at a air conditioning system, like we did on the very first day of this class, on your introduction day, air conditioning systems have compressors, they have heat exchangers. Power plants have pumps, they have different heat exchangers, cooling systems. All of this directly relates to what we're about to talk about now. So what I would like to do, and this is different than the way they do it in the textbook, what I would like to do is I want to actually derive the first law for an open system from the first law for a closed system. I mean, I feel that's the best way to do it because we already understand the first law for the closed system. So let us derive the first law for an open system from first law for a closed system. Now, this might be a little confusing. I'm going to do my best to try to make it all understandable. Hopefully it will be. So first I want to start with a drawing. And let's just say we have some initial and final state. Let's just say that we have this control volume, and it's going to be the same control volume, but we're going to undergo some process, and we're going to end up over here. It's the same control volume. These two shapes are supposed to be the same, even though on my diagram this one has a little leg over here. They're supposed to be the same. And then what I want to do is I want to remind you that the dashed line represents the boundary of the open system, right? This is our control surface, as it's sometimes called. So the dashed line, where should I put that? Dashed line is the control volume boundary. And then I want to overlay this with a closed system. So the closed system is going to look like this, and it's not quite the same. There's a little bit of fluid which is coming in on the left-hand side, which is going to be part of the closed system. Otherwise, these two lines overlay each other directly. So you've got this little hump, if you will, over here on the left that's about to flow in. Now, I can't show the dashed line and the solid line directly on top of each other. You would not see the dashed line, but they're supposed to be on top of each other again, except for just this little bit that's about to flow in. And then the process occurs, and the flow in occurs, and now a little bit of fluid that previously was inside the control volume has now popped out the other side. So when we show the closed system at the end of this process, well, again, the open and closed system boundaries completely line up with each other except for this little bump of fluid that pops out on the right-hand side. So the solid line then represents the closed system boundary. Now, we will note that this little bit of fluid that's over here that's about to come in has a certain incremental amount of mass associated with it that I'm just going to call dmi, I for inlet, because that's about to flow in. And then over here on the exit side, the little bit of mass that pops out, that incremental amount of mass, I'll just call dme for exit. And there's going to be a certain amount of energy associated with that little bit of mass that's about to flow in. I'm going to call that E sub I, lowercase e, so it's energy per unit mass at the inlet. And there's a little bit of mass that pops out, and it's going to have a certain amount of energy per unit mass that I'm going to call E sub E. And this process occurs over a very small time frame. So this process over time, and that time frame is just going to be dt. So over some very small incremental amount of time, a little bit of mass flows in, and a little bit of mass flows out. We might note that the mass that's about to flow out, we can kind of show in a little cloud over here. It doesn't really matter if you show this on your diagrams, but that's what's about to flow out. And then once that mass pops in, that little bit of mass that pops in, I guess we could show it as a little cloud over here. But it's completely within the system, and it's completely within the control volume now as well. So this is the setup. This is the diagram that I'm going to use. And next, let me define a variety of terms for you. So for the closed system, we'll note that E1 and 1 would represent the initial state of the closed system. So the initial energy of that closed system is really going to be the energy associated with the open system, right, the big oval, plus the energy associated with what's about to flow in. Remember that the two line up entirely, except we've got a little bit of that closed system which is about to flow into the open system. So E1 is just going to equal ECV1. That's going to be the energy associated with the open system initially, and then again plus that little bit of energy that's about to pop in. So that's EI dmi. And after time dt, the final amount of energy within the closed system, well, again, you can see that closed system is a little bit bigger than the open system. That's going to contain all the energy of, well, the control volume, the open system, and then plus that little bit of energy that's just popped out. So plus EE, EME. So we're generally interested in finding the change in energy for a process. So we'll write this as E2 minus E1, which we can just show as dE if we want to. It's just a small incremental change in energy. And this is just going to be the difference between, well, this is the difference between the initial and final energy of the closed system. Remember, this is for the closed system we're looking at now. So just plugging in from above, we would get ECV2 plus EEDME minus ECV1 plus EIDMI. Or we can just rearrange this, and now I'm actually just going to drop the E2 minus E1 notation. I'll rearrange this, and I'll have ECV2 minus ECV1. So those terms are going to connect together. And then plus EEDME minus EIDMI. So that's what I've done to rearrange this particular equation. Now, this right here, this ECV2 minus ECV1, I'm also going to just let it equal dE, but this time I'm going to put a little CV as a subscript. So this dE on the left-hand side of the equation is the energy change over this brief time frame associated with the closed system, and then the DECV is going to be the incremental energy change associated with the control volume, or the open system, if you will. So let's just finish plugging these in. All right, so we have that equation. Oh, you know what? I put a couple extra brackets in there. Oh, well. I never have too many brackets, right? So now what I want to do is note that this is shown in its incremental form, if I wanted to, I can show this in the form of a time derivative. So if we just take the time derivative of this above equation, we basically get the e dt. So the change in the closed system energy with respect to time is going to equal dEcv dt. In other words, a change in the open system energy with respect to time. And then plus, and here, whatever the energy is exiting or the energy associated with the system entering, that doesn't change. That's just some value. But the mass is changing, right? There's a certain amount of mass flowing in and mass flowing out. So we would then rewrite this as just EE dme dt and minus DI dmi dt. So this is equation A. And it's really interpreted the same way as we've been interpreting this all along, right? The change in the energy of the closed system equals a change in energy of the open system plus the energy that goes out less the energy that comes in, right? So we're taking into account the flow of energy in and out as well as the change in energy within the system itself. Now I'm calling this one equation A, and I'll get back to it here shortly. Next, what we want to do is look at the work. Now, there's really two types of work associated with this problem. Okay, one is going to be what I'll just call miscellaneous work. And this miscellaneous work is just going to be written this way, delta W CV. So this is the miscellaneous work associated with the control volume. And this is going to be based on, well, mechanical inputs or outputs. So in other words, we could have shaft work, like on a pump, right? You have a metal shaft that is connected to a motor, and that metal shaft spins, and that spinning shaft is work input. We could have a turbine where a fluid is passing over the blades and causing rotation on a metal shaft, and that would be output shaft work, right? You'd hook up that spinning shaft to an electric generator and produce electricity. Maybe it's a mixing device. That's a mechanical form of work. Maybe it's electric resistance work. So it's all these different types of work, which we'll just categorize as miscellaneous work. That'll be shaft work, mixing work, I'll just put etc. So any work associated with mechanical inputs and exits is going to be this just delta W. And then the other type is going to be our boundary work. We know that whenever we have a change in volume, there's going to be boundary work, right? And there's definitely a change in volume. I mean, if we go back up here to this diagram up top here for a moment, we start with the volume with a little bump on the left, and by the end of the process, the volume has shrunk on the left-hand side, and the volume has increased on the right-hand side. There's nothing that says that the two of those are going to be equal. We don't know that for sure. In fact, it probably won't be equal. So we're going to have to consider the boundary work associated with the volume change on the left input and the boundary work associated with the volume change on the right, which is your output. So how do we consider boundary work here? Right, so let's just continue. So the fluid in and out has boundary work associated with it due to the volume change. It's always going to be the case for boundary work. So how do we consider that? Well, we've already seen the equations for boundary work. I mean, just because we're dealing with an open system as well as a closed system doesn't mean that the nature of our boundary work changes. So we would note that in its incremental form, any incremental amount of work, again, this is boundary work, is just pressure multiplied by the change in volume. However, we would also note that the change in volume can be written as the specific volume multiplied by dm. I mean, in the same way that mass equals volume over specific volume, an incremental amount of mass would equal the incremental amount of volume change over the specific volume. So all I've done here is I've replaced this dV with the specific volume times dm, and therefore my incremental amount of work is just going to be pressure times specific volume times the mass. Well, times the incremental amount of mass. All right. Now, we have to note that this is just a general equation, right? We have boundary work both at the inlet as well as at the exit. So, at the inlet, we're going to say that this is dwi, and this is going to equal pi di dmi. Please note that I left a little space here on purpose because we have to consider our sign convention. We know that when work is being done to the system, that the work is considered negative, right? And work is being done to the system, right? We're starting with mass that's outside and we're moving it into the system. The volume is shrinking, so this would actually be negative work, okay? Negative because work is done to the system. And at the exit, we would show that delta WE is going to equal PE VE VME. Now, there's no negative sign here, right? The work is being done by the system to the surroundings as the system pushes that little increment, that little bump of work, I'm sorry, that little bump of mass out of our control volume. All right, so, yeah. So this gives us two equations for incremental amount of work. And then now what we can do is we can say that the total incremental work is just equal to delta W, where delta W then is going to equal the sum of the miscellaneous work, which is what we talked about above, based on these mechanical inputs or outputs, plus the work associated with boundary work, in other words, plus PE, VE, whoops, that's the specific volume, VE, DME, and then minus PI, VI, DMI. Okay, so all I've done is add together the miscellaneous work along with the other two boundary work terms. Yes?
Yeah, the fact that you wrote two different subscripts for the specific volumes for the in and exit, does that mean that we could have problems where the specific volume changes as it goes through the process?
Well, you will have every problem where the specific volume changes. The only time it won't change is if it's an incompressible fluid, and that's going to be rare. There will be maybe one or two problems you'll see, but no, in general, the whole thermodynamic state changes. I mean, if you have a pump, you're doing work on that fluid, right? Whatever the state is coming in, you do work on it. The pressure is undoubtedly going to increase, the temperature is going to change, the volume is going to change. I mean, everything's going to change. So you definitely are going to have a different thermodynamic state at the inlet compared to at the exit. All right, so now what we want to do is kind of like we did with that energy equation. We'll just write this as a differential with respect to time. In other words, let's take the time derivative. So we get delta W dt equals delta W for the control volume dt, and then plus, and then here what we would have is PE VE PNE dt, and then minus PI VI DMI dt. And this equation I'm going to call equation B. Now, we have the equation, the general equation for energy. We have the general equation for work. Now let's go back to the first law So, the first law for a closed system, and this has many different forms, but I'm going to write this in its differential form with respect to time. We can write this as del Q dt equals the E dt n plus del W dt. Okay, this is just one of, I think, 3 or so different forms of the first law, right? The heat transfer, well, in this case, the rate of heat transfer equals the rate change in the energy of the system plus the rate change of work. Okay. And then what we want to do is plug in A and B from above. So if we plug in A and B, we would get the following. So we have del Q dt equals, and then first we would have the substitution of equation A. So this says dE dt for the control volume plus EE dme dt minus EI dmi dt. And then we would plug in equation B, which is the work equation. So this one is dW dt for the control volume, and then plus all these other terms, so PE, VE, dme dt minus PI, VI, dmi dt. Okay. And then, oh, actually there's no and then. So this is the equation. And then I want to rearrange. So rearranging the equation, I'm going to keep the heat transfer term on the left-hand side, but I'm also going to put all the various inlet terms, the dmi dt, PIVI, and the dmi dt EI term, I'm going to put those all together here on the left. So plus dmi dt, and then we would have EI plus PIVI. And on the right-hand side of the equation, first we have the energy change of the control volume with respect to time. And then I'm going to collect together all the dme dt terms. So EE plus PE, VE. And last but not least, we have our miscellaneous work, so delta W dt for the control volume. Okay. I need to move this. All right. Now, let's recall that energy is equal to internal energy plus kinetic energy plus potential energy. Now, this would be written on as a total basis, but on a per unit mass basis, so I'll put in or, we can write this as energy per unit mass equals the specific internal energy, which is the internal energy per unit mass, and then plus E squared over 2 plus GG. Okay. And this equation, again, is just a general equation, right? It's going to apply at both the inlet and the exit. So what I want to do is apply it at the inlet and the exit and plug it in above. So I'm going to plug it into the equation above, and we would basically get the following. So del Q dt equals, and now we have these dmi dt terms, and now instead of just E plus PIVI, we're going to have ui plus vi squared over 2 plus gzi plus pi vi. And in fact, I'm going to write it this way. I'm just going to reorder the terms. So I'll put ui plus, and now I'm going to take the pi vi term from within that bracket and just move it here. And then plus vi squared over 2 plus gzi. So we've applied it at the inlet. And then we have the energy change for the control volume, and then plus the dme dt term. And then again, I'm substituting the same equation in at the exit. Yes?
On like the second line from the top page, you have it equals, and then it becomes a plus equal, and then back down here it's an equal, and then
So I made a mistake somewhere?
I just want to.
So where are you saying they have a plus or equal?
So
To the
right,
left.
it's equal, and then if you drop,
I mean, this is an equal?
yeah, and then if you drop down, that's a plus.
Yeah, because what I've done is, note that this is a negative
Okay.
EI DMI dt, so it comes over to the left-hand side as a positive, and this is also a negative PI VI DMI dt, so it comes over to the left-hand side as a positive. So that's why I have a positive, and then I have an equal sign.
And then if
So,
you go back down.
Oh, I see, so down here, yeah, right, that's a plus.
Okay.
I guess that was the whole confusion.
Yeah.
Yep, plus sign, sorry about that. Anyway, so let's get back to this dEdt term. So we have dme dt, and then again, we have all the same terms we had over here. We have ue, and then again, I'm just going to rearrange. I'm going to put the PEVE term next, and then VE squared over 2 plus GZE, and then last but not least, we have our delta W VT for the control volume. Now, this particular equation can be modified based on our understanding of the definition of enthalpy, right? We know that by definition, U plus PV is enthalpy. So this is HI, and here this UE plus PEVE, this is HE. So let us just rewrite again. So we have del Q dt plus dmi dt, and then times hi, whoops, I moved that up, plus vi squared over 2 plus gzi equals dEdt, control volume, plus dme dt times he plus VE squared over 2 plus GZE, and then plus work. So delta W dt for the control volume. And then I would like to note that we can use the dot notation. So let's use the dot notation for a time derivative. And we're going to do this for the inlet and the exit. So let's rewrite this another time. So we have delta Q dt plus, and now we'll just have m dot I hi plus vi squared over 2 plus gzi equals the EDT for the control volume plus m dot E HE plus DE squared over 2 plus GZE, and then delta WDT for the control volume. Oh, I'm sorry. Oh, no, that's right. Yeah, we'll just leave it this way. And then I want to do one more thing. Let's apply the same dot notation to the heat transfer and the work terms. And what I also want to do at the same time is note that we could have numerous inputs and exits, right? There's nothing that says that we have to have just a single inlet and exit. I mean, certainly there'll be a lot of single stream steady flow problems that we're going to analyze, but we have to leave the possibility open for multiple streams, don't we? We could easily have like a heat exchanger where we've got 2 inlets and 2 exits. Now, I don't want to have to go through this entire derivation because it took a while. By putting like 2 bumps on the inlet side and 2 bumps at the outlet side, we can go through exactly the same process and we would end up with exactly the same terms, but instead of just a single inlet term, we would have multiple inlet terms, and instead of a single exit, we'd have multiple outlets. So I'm not only going to apply the dot notation to the heat transfer work terms, I'm also going to include the possibility of multiple inlets and exits. So, and include many inputs and exits. Now, in doing so, all I have to do is put a summation sign in there. So I basically get the following. I get Q dot plus the sum over all inlets of M dot I HI plus VI squared over 2 plus GZI equals the EDT for the control volume plus, and now we have a sum over many exits of M dot E times HE plus VE squared over 2 plus GZE plus W dot. Let's just put a little subscript CV on both the heat transfer and work terms. I mean, by the way, the control volume is entirely within the closed system, right? So any heat done to the control volume is done to the system. Any work done to the control volume is the work done to the system. So this would now be the final form of my equation, and I'm essentially done with the derivation. So this equation is the first law for the control volume. And it's this equation that we're going to use over and over and over again for all of these different types of problems. Okay. Now, let me just tell you that I am never going to ask you to go through this derivation on an exam. I just wanted to make sure you knew where this equation came from. I felt that if I just gave you the equation, that would probably provide or lead to more confusion than if I were to derive it. At least we know that this is a valid equation. Now, you may have to go through the derivation and convince yourself that I've done all the right steps in the right order and that it is indeed accurate, but this is the first law for control volume. Now, I want to just end it here. You've got a test on Monday. I wanted to talk a little bit about the midterm and see if there's any last minute questions I can answer. So let's just leave it at this for now, and then I'll talk a little more at the midterm. By the way, we're not really done with this. I mean, yes, this is the appropriate equation for the first law, but there's many simplifications. If we have a single stream process, this changes. If we have a steady flow process, this changes. So I do want to derive the other and arguably more useful forms of the first law for steady flow processes, or first law for control volumes, by looking specifically at steady flow processes, single stream steady flow processes, and then there'll even be some other processes that are not steady flow that we're going to talk about. But for now anyway, this is all the time there is, so let's just leave it here. So, about the midterm then. By the way, any last questions on this derivation before I move on? All right, so about the midterm. First of all, just a reminder that it's on Monday. Please be on time. You'll have the full hour and 5 minutes. It'll be right here in this classroom. The material will be anything through last week's material. Nothing from this week is going to be on the midterm. So that'll basically be through last week's homework that you turned in Wednesday and just have returned to you today. So don't forget to pick up your work. It could be anything from very basic, simple problems, like, maybe I'll give you some properties and you'll have to tell me something about the state. Is it a two-phase mixture? Is it superheated? Is it compressed? I may have problems where I give you some properties and ask you to find the other properties. Maybe I give you pressure and temperature and you need to find enthalpy or internal energy or specific volume or whatever that might happen to be. So there may be some simple problems like that. There may be problems that involve the ideal gas equation of state, as well as problems that involve the compressibility chart for gases. With regards to other types of problems, there will certainly be an emphasis on the use of everything that I've just mentioned. In other words, you will see probably two closed system problems, not different necessarily, at least not too much different than the kind you've seen in this last week's homework set, again, the one that you're picking up again today. So you need to know how to use the first law. You need to remember that heat transfer equals the change in internal energy plus the work, well, plus kinetic and potential energy, but every single problem we've seen, we've neglected those, so in all likelihood you'll neglect those as well. You'll have to know how to calculate work. Boundary work is certainly very common. For constant volume problems, it's easy, it's just 0. For constant pressure problems, it's P times change in volume. You may also have a polytropic process that you're going to have to analyze, so make sure you understand how to calculate the work for a polytropic process. That will be necessary as well. And then let me also note that I don't want you to memorize the various miscellaneous work equations. You know, we've looked at work for, let's say, electrical resistance. If you have a problem like that, I'll give it to you. If you have spring work, I'll give you the spring work. If you have shaft work, if you have mixing work, I'll give you those work terms. So you're not going to ever have to calculate those. I think those are described in more detail in section 2.4 or 2.5. But you know, I just kind of glossed over those, and I'll do the same thing. So, you know, you want to key in on the understanding of the first law, know how to solve the first law problems, understand your sign conventions, understand your units, know how to get your data out of the appropriate tables, know which tables to use. In a case where you have a gas, know how to check whether the gas is an ideal gas or not. And if it is an ideal gas, know how to use the ideal gas equation of state, PV equals nRT. If it's not an ideal gas, then basically PV equals Z nRT, right? Or if you will, PV over RT equals 1 for an ideal gas, or it equals Z for a real gas. How to use a compressibility chart. So any of that could certainly be fair game on the exam. I'll give you the property table handout that I have. If anybody owns the property table booklet, we used to sell the hard copy of the book in the library, in the bookstore, and then along with it came the separate property table handout. If you have that, bring it. That's fine. If you don't have one, I'll pass out the tables that you need. So you will have all the property data you need. But it is a closed book, closed notes exam. You're not going to have a note sheet. You will probably, well, you'll definitely have to at least memorize certain equations like the first law, like boundary work, like ideal gas equation of state. You'll certainly have to know how to use tables. You have to know how to use quality to find properties. So, you know, make sure you're well prepared. Is there a question?
Is there anything that are the sheet that you'll give us online on Blackboard so that we can see it before the exam?
You mean the actual data sheets?
Yeah.
Well, it's really
Just
not,
more
there's
data.
no equations or anything. It's just the same data that's in the appendix of your book.
It's like the whole 100 pages?
No, it's just the tables that are going to be useful, or I should say the ones that will be necessary. I mean, I can show you what it is. It's the same thing that I've been pulling up. So it's just this thing. I call it property table handout, but basically, you know, that has the cover you'll see. It's from the 8th edition, and then I have a little table of contents, and this shows you everything. Table A1 really through A7, and then A11 through 13. I also include table A17, but you won't need that, not until ME302. And then the compressibility chart is on there as well. So it's the same stuff that you have in the back of the book. So there's nothing new or different. Just a full collection of everything. Yeah. Although I've copied it, just to save paper, I've copied it like 2 pages to a page. So the numbers are kind of small. If anybody has eyesight issues, then, you know, bring your bifocals, or just bring a magnifying glass or something like that if you need it. I mean, hopefully you won't need it, but if you do, it's better to have that just in case. Any other questions? Any questions on homework problems or methodology or?
So, are you saying that you need to find the work by polytropic process, just memorize if it's n equals 1, there's this one, if it's not?
Yeah, right. I mean, if it's n equals 1, it's P1 V1 times natural log V2 over V1. If n is anything else other than 1, it's P2 V2 minus P1 V1 over 1 minus n. So they're not difficult to memorize, but, you know, you will have to memorize them. Yeah.
Along in chapter 2 are some formulas for efficiencies of different.
Oh, no, don't worry about efficiency. I mean,
I
I did
noted.
mention it, and I think maybe I assigned one homework problem back then, but
Yeah.
no, that's not important at this point. We will be dealing with efficiencies as we start getting into the second law of thermodynamics, but that's not really for a couple more weeks. So no efficiency stuff. Any other questions? Okay, great. Oh, here's one, yep.
We're gonna need to know the compressed, not compressed, really the quality.
Oh, absolutely. I mean, you could definitely have a problem that has a two-phase mixture. So, just remember U equals UF plus quality times UFG. And the same thing for volume or enthalpy or entropy or any property. Just the saturated liquid plus the quality times the difference between vapor and liquid. Yeah, anything you used in all these various homework problems, you should be prepared to use. Okay, anyway, good luck studying. You're allowed to take a break from 3:30 until 6:30 to watch the Super Bowl, but otherwise you should be studying hard all weekend, right? Okay, have a good one. I'll see you guys all on Monday. Again, be on time.